let's say I have 1 molar of, let me pick a strong acid. Let's say it's hydrochloric acid. Hydrochloric acid, HCl. And we know, of course, that since it's a strong acid, it dissociates completely. So HCl in an aqueous solution or solution of water dissociates completely into hydrogen ions in an aqueous solution, which is really hydronium. I've said that multiple times. Plus your chlorine anion in an aqueous solution. So if you actually have a molar of this, as soon as you put it in the water, you really have 1 molar of this. So your hydrogen concentration is really 1 molar. And of course, we know that what's the pH of that? Well, the pH is just the minus log base 10 of your hydrogen concentration, which is 1, which is the minus log of 0. So minus 0, which is equal to 0. So your pH is going to be equal to 0. And let's say for use in the later part of this, let's say I have a liter of this. Right? This just tells me how many moles per liter. And now I just told you that I have 1 liter. So you know that you have 1 mole. So let me make a little chart here. I'll make a little box here. And let's make this axis right here. This is going to be my pH. And right when I take that first measurement, let's say this is 0 here, this is 7, and this is 14 up here. When I take that first measurement, my solution of hydrogen chloride or hydrochloric acid has a pH of 0. Now what I'm going to do is I'm going to titrate this acid, this aqueous solution of acid. And titrate just means drop something else into it in controlled increments to see what happens. And this is called an acid. What I'm doing here is going to be an acid-base titration. I have an acid here, and what I'm actually going to titrate it with, or the reagent that I'm going to add to it, and the word reagent, the reagent is essentially a reactant that when you view it this way, that you're adding to the solution. So it's the titrant. So in this case, my solution already has hydrochloric acid in it. The pH is already 0. But what I'm going to do is I'm going to add a strong base. I'm going to add a strong base. Let's say sodium hydroxide. That's my favorite strong base. And let's say I have a solution that I have prepared ahead of time. Let's say it's a 1 molar solution. 1 molar solution. But I'm not going to add all of it at the same time. I'm going to add it in increments of 1/10 of a liter. So let's say so this is 1 liter that I've added it. And then this would be 2 liters. So this would be 500 milliliters. 500 ml. This is 1 liter. This is 1.5 liters. This is 2 liters. And so on this axis, I'm going to slowly add more and more of this hydroxide. So what's going to happen? As I add, let's say I add 5. As I slowly add hydroxide, it's going to increase the pH. Why is it going to increase the pH? Because this OH, remember, hydroxide is a strong acid, a strong base. So the NaOH dissociates completely in an aqueous solution to OH minus plus sodium cation, right? Now, if I'm adding this to this stuff here, what do you think is going to happen? Well, this stuff right here, these OHs are just going to sop up your hydrogens. So for the most part, obviously everything is probabilistic, and whenever we're dealing with chemistry, there's always some molecules that won't completely react, and there'll always be some concentration of anything. And that's why you actually can never get to a 0 concentration of hydrogen, no matter how much base you add, because there'll always be some hydrogen molecules that are just hiding just perfectly, or they're in perfect equilibrium, so they don't react. But most of them will react. But so as I add more H, these are going to disappear. So my hydrogen concentration is going to go down. The pH is the negative log of that, so your pH will go up. Your pH will go up. Slowly. Well, it'll look slowly because it's a log chart, so maybe it's doing something like this. Your pH concentration is going to look something like as you add more and more. But you might say, oh, that's such a slow movement. Why isn't it occurring faster? But you have to think about something. This right here, if this is 1, if this is a pH of 1, this means, so at a pH of 0, this means your hydrogen concentration is 1 molar. At a pH of 1, this means your hydrogen concentration is at 10 to the minus 1, which is 0.1 molar. So even though on a log chart it looks like you've made a very small movement, you've actually gone by a factor of 10 in terms of your reduction of your hydrogen concentration. So roughly, by the time you've added, you started off with 1 molar of your hydrogen. By the time you've added roughly 900 milliliters of your solution, you probably would have gotten rid of most of it. And obviously the denominator is changing because I'm actually adding volume here, right? Because I'm actually adding some volume here, so you'd have to add them. But you get the general idea that these actual molecules of hydroxide are going to react with these things. They're going to essentially turn into water and disappear into the solution, but it's going to lower so these are going to disappear with those disappearing for the most part, which leads in an overall reduction in concentration of your hydrogen ions, which will lead to an increase in your pH, until some point where you've pretty much sopped up as many of these things as you can. There'll always be a few of them, but you've sopped up as many of them as you can. And so any incremental hydrogen you add, or any incremental hydroxide you add, will actually go to build the hydroxide concentration, where the hydroxide concentration is going to be greater than your hydrogen concentration. But even better than that, there's going to be some point where you've added just enough of this that you have an equal amount of this and this. You have an equal amount of hydroxide and hydrogen, right? And if you think, well, what happens, first of all, when there's an equal amount of hydroxide and hydrogen? Well, then you're neutral, right? If your hydroxide concentration is equal to your hydrogen concentration, you're neutral. This is just like water. You're at a pH of 7. So there's some point where your hydroxide concentration is equal to your hydrogen concentration, and your pH is going to be 7. And then above that, you're just adding more and more hydroxide. The hydroxide concentration is overwhelming your hydrogen concentration. And so you're going to get really, really basic. And since this is a strong base, you're eventually going to get to a pH of 14, because you're essentially going to have, well, you're not going to have 1 molar. Let me erase that point. You're going to have half a molar of OHs at the end of this. So your graph is going to look something like this. It's going to look something like this. This is when that's kind of, you can kind of view that as, and up here, now, I mean, you're still going to have hydrogen concentration, but it's going to go really small. It's going to get really, 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 really small. Now, what's interesting about what just happened here? At this point right here, your OH is equal to your hydrogen. And the way I think about it is, or the great majority of your moles of hydrogen were sopped up at that point. So in order to sop up 1 mole of hydrogen, you essentially, for the most part, and these are, there's always things that don't get completely sopped up, but you'll essentially have to add 1 mole. So you're essentially going to have to add 1 mole of OH to sop up your 1 mole of hydrogen. Remember, this is 1 molar, and you had 1 liter of it. So you had 1 mole of hydrogen to sop up. 1 mole. So you need 1 mole of OH to sop up. And how do you get 1 mole of OH? Well, we said that the concentration of this solution was 1 molar. So once you put a liter in there, because that's 1 mole per liter, once you put a liter in there, you would have put 1 moles of hydroxide cations in there to sop up the hydrogen. So this was the point. This is the equivalence point, where you have an equal amount and very low concentrations of both hydroxide and hydrogen. You've essentially sopped up all of the hydrogen, but you also have sopped up all of the hydroxide that you've added so far. After this point, any hydroxide you add will essentially contribute to increasing the pH even more, or it'll kind of overwhelm your hydrogen concentration. Now, what's interesting about this? In this example, I told you, oh, I have hydrochloric acid, and I gave you its concentration ahead of time. But let's say I didn't tell you that. Let's say it was some mystery substance, and you just measured the mystery substance's pH at this point. You said, okay, its pH is 0, and you titrated it with this sodium hydroxide. And you said, gee, when I added 1 mole, because you figured out at a liter of this solution, I've added 1 mole of hydroxide ions. At that point, I've essentially eliminated all of the hydrogen ions that were in my original solution. So I must have had 1 mole of whatever acid this was over here. So this would have told you that my initial concentration was 1 mole of H+. And since we know it's easy to see how much volume you have, you say I have a liter, so you say, oh, my original concentration of this acid is 1 molar. And you can also know that what you're dealing with is a strong acid. Because it's a strong acid, and maybe this will, and I encourage you to watch the next video where I do the same thing with a weak acid. But because it's a strong acid and a strong base reacting with each other, when you have the same number of moles of both, you get exactly to a pH of 7. They completely neutralize each other, and you have a completely neutral solution. If you had a strong base with a weak acid, the strong base, once you have the same amount as the weak acid, it would have neutralized it, but you would have also had some of the conjugate weak base left. So you would actually ended up with a basic pH, and I'm going to do that in the next video. But if you see that the equivalence point, the equivalence point occurs at a pH of 7, you know that you were titrating, what you were dealing with was a strong acid, because it was completely neutralized, not more than neutralized, by the strong base. And what you do is you look at and if you want to eyeball where is the equivalent point, you look for the steepest point in the graph, because that's the point where you're going from having a majority of hydrogen versus hydroxide to having a majority of hydroxide versus hydrogen. So it creates this inflection in the graph, and you just would have to look at this chart and say, oh, I added a liter of this solution. The concentration of this solution is 1 mole per liter. It's 1 molar. It has a molarity of 1. So I must have added 1 mole of hydroxide to get to this point. So I must have neutralized 1 mole of hydrogen. So there must have been 1 mole of hydrogen to begin with. 1 mole of hydrogen. And since I had 1 liter of solution, I had 1 mole of hydrogen in 1 liter of solution. So my original molarity was 1. Anyway, I don't want to confuse you too much. In the next video, I'm going to try to do the same thing, but I'm going to do it with a weak